Yeah, you can start.
Yeah. Start with the presentation.
So welcome everybody. This is the third lecture. So Sanjay.
Yeah. Okay, so yesterday we derived this. Sorry. Yeah. Yesterday we spent some effort deriving this TGGR equation or model A as it's called in dynamical critical phenomena. So today we'll, at least in the first lecture, we will sort of do some simple calculation of this equation. Okay, that's my target for today. But first, I want to spend 5 minutes answering any doubts that may exist from yesterday, from yesterday's lectures. And I mean any doubt is welcome because if you have a doubt, most likely a few other students also have the same doubt. Okay, so we move on then. Huh? Oh. Okay, so yesterday, let me just sort of refresh you what we did yesterday. We derived this DDGL equation from the master equation. So DDGL equation uh, or model A. Uh, Again, I'll emphasize that these were first written down in the context. So let me write down the equation. In its dimensionless form, it's del psi by del t is equal to psi minus psi cubed plus h, which is the magnetic field, plus grad squared psi. It's a classic nonlinear partial differential equation, and in general, you can't solve the initial value problem. Equation, I've already sort of figuratively told you what the dynamics is. Basically, you have a local free energy G psi, and below the critical temperature, you have uh, extrema, two minima at symmetrically located magnetized states. So that's minus psi 0 and plus psi 0, and a local maxima, which is obviously also an extrema, at 0. Okay, and of course, in this dimensionless language, psi 0 is just equal to 1. Basically, I just use the scale of order parameter to kind of set that as equal to 1. And the phase ordering problem is you start off with a spread of order parameters around there, order parameter values, random fluctuations, and then you relax either into this or this ground state. The system is pretty happy to be in any of the ground states, so they compete with each other. And the competition process is what's called domain growth. There's a process of one domain finally winning out over the other. And it's a random sort of process. Sometimes one species will win, sometimes the other species will win. Okay. So I also did this linear stability analysis yesterday around 0. So we considered psi is equal to 0 plus delta psi RT, and we found that all modes, so all modes with it, again, now I'll only talk in dimensionless language. All modes with magnitude of k vector less than 1 grow exponentially. And if they grow exponentially, I mean, obviously, any arbitrary delta psi, any initial fluctuation, will have some modes with k less than 1. So any initial fluctuation will be amplified in time. And the sort of picture I drawn, and that sort of could be last recall from yesterday. So you're plotting the order parameter psi along some one direction, for example, x. You start off with small fluctuations around 0. Let's just sort of small fluctuations, amplitude fluctuations. That corresponds to a ferromagnet before the quench. These are amplified. There's some sort of amplification process, and this is generic to all many pattern formation phenomena. And finally, the non-linearities kick in, and these guys settle into domains of +1 and -1. Okay, the two equivalent domains. So basically, the system is happy almost everywhere except at the interfaces. And so the last process, the domain growth process, is the annealing of these interfaces of peaks, their collision, their sort of and the growth process. And that growth process has a growth law associated with it, which is generically p raised to the power half. There are logarithmic corrections in marginal dimensions. Marginal dimensions is where the defects become point defects. Okay, okay. So the next thing I want to do, remember, just keep in the back of your mind my overall sort of goal. My overall goal is to capture the dynamics of this nonlinear PD. Okay. Obviously, as I said at the beginning, if it were solvable, that would be wonderful, right? But it's not analytically solvable. So now I'm going to use approximations, and the natural approximation is to identify what these interfaces are doing. Okay. So as I said, I'm in equilibrium here. I'm in equilibrium here. What is the interface between the sort of two equilibrium states doing? And I'm going to spend a few minutes doing that calculation. Okay. So now I'm going to look at what are called static interfaces or kinks. Okay. And it turns out that these kinks are also static solutions of the differential of the PDGL equation. Okay, so I'm going to basically look at the solution. I'm going to look at a solution which it's obvious from the kinks that goes to, let's say, -1 at z going to x go to minus infinity, and +1 at x going to plus infinity. That's the sort of solution I'm going to look for. So I'm going to look for a static solution of this equation. Let me sort of distinguish it by putting a subscript s. So it's going to be psi s minus psi s cubed. I'm working with a case where magnetic field is 0. Magnetic field non-zero is not a very interesting domain growth problem, because then one of the domains is preferred over the other. Plus, I assume a variation in just one direction. d2 psi s by dz squared is equal to 0. Okay. I claim there's a static solution of that kind, and now I'm going to spend a few minutes seeing whether there is actually a static solution. And what do you expect the static solution boundary conditions to be? That you expect that psi s at plus infinity is, let's say, +1, or psi s and psi s at minus infinity is equal to -1. Okay. That's the kink solution that I'm going to look for. Obviously, there's also an anti-kink solution which will solve this equation, but with that being -1 and that being +1. So that's right there is an anti-kink as a matter of fact. But if you get one, you can get the other, basically. Okay, so how, any suggestions how we solve this equation? So I can only sketch what the solution is going to look like. The solution is going to be, if I just sketch this kink, psi s as a function of z goes from -1 at z equal to minus infinity to +1 at z equal to plus infinity, basically. Okay, and the width over which it changes from one to the other, which is where the system is essentially unhappy with its state, is going to be determined presumably from the equation. Did anybody try to solve this equation? I remember this was what I given you as a parting sort of homework problem. Did anybody attempt it at the evening? Okay, no problem. Students never do homeworks, right? So how do we solve this equation? Suggest something. What comes to mind immediately? By the way, this is a very standard equation in field theory. Okay, this is I mean, people often sort of solve this equation. Okay, I hope it's clear to you that the energy of this will be higher than the energy of the homogeneous solution. Okay, that should be clear to you. I'll calculate it explicitly, and the difference between the energy of this solution and the homogeneous solution will actually give me the surface tension, right? Because here it's homogeneous, here it's homogeneous. The difference is only in the surface of the interface. Okay, so the way to solve this equation, the next time you sort of encounter it, is to multiply both sides by d psi s by dz. Okay. Actually, this is a technique you should know. It's a nonlinear equation, so you can do a first integral by multiplying everything by d psi s by ds. Let me just write down the answer, and then sort of you can immediately convince yourself it's true. So this is d by dz half d psi s by dz the whole squared plus psi s squared by 2 minus psi s 4 by 4 is equal to 0. Does everybody agree with that? I claim that's a first integral. The only slightly tricky term is this guy, and if you just take the derivative of that, you'll find you get this guy multiplied by this. And the other terms are sort of obvious, basically. Okay? So that's very nice. With almost no effort, I've been able to do a first integral. And what is the first integral saying? That this guy is a constant, basically. Otherwise, how would it be d by dz equal to 0, right? It's a constant. What is the value of that constant? How do I determine that? Help me with that. I use the boundary conditions, basically, right? So what are the boundary conditions? When sort of z goes to plus, let's take it plus infinity. This guy is 1 over 2 minus 1 over 4. That gives me 1 over 4. What is this guy? What is the derivative of psi at infinity? 0. It's flat as a matter of fact, right? I have a homogeneous phase at z equal to infinity. So that's just 0, and that gives you your answer. So the constant is simply 1 over 4.
The derivative being 0 at infinity, that's also part of the boundary condition?
No, that's not part of the boundary condition. That's part of the physics of how you sort of normally solve for these. Okay, so that's the solution right there. And let's write this down in sort of on this bit of board here. So it's half d psi s by dz squared is equal to, well, let me write it down still in this form, psi s squared by 2 minus psi s by 4 is equal to 1 by 4th. Okay, that's the first integral. I've gone from a second derivative to first derivative. Very nice. Now, I hope the solution is obvious. Probably you guys haven't solved a differential equation for a long time. So, so this becomes, let's write it this way. This is equal to minus this plus this plus this, basically, right? That's the differential equation. The next thing you do, and this, if you realize, it will just take a little effort, just multiply by 2 throughout. So then let me do that also on this equation itself. Multiply by 2 throughout, that's 2 gone, that will become 2 there, and that will become 2 out there. Basically, I hope this is correct. Have I made a mistake somehow? No, sorry. I have to multiply by 4 throughout, okay? So that's 2, that's 2, that is gone now, and that is gone now. Okay, I multiplied by 4 throughout, not 2. Okay, and this of course is nothing but 1 minus psi s squared, the whole squared, right? Pretty sort of straightforward stuff. Now you take the square root on both sides and you find that square root 2 d psi s by dz is equal to either 1 minus n psi s squared or alternatively psi s squared minus 1. Okay, by the way, you often have to derive such, if you do field theory, you often have to derive such sort of soliton type solutions. Why do I have two branches? One is going to give rise to the kink, one is going to give rise to the anti-kink, basically. Okay, so if you impose the boundary condition, then one of these branches disappears. Do I need to go further, or can you tell me the solution right now? How would you do the rest of it? Huh? So basically, let's consider the kink solution that arises from d psi s by dz is equal to क्या है? 1 over square, sorry, d psi s by dz is equal to 1 over square root 2, 1 minus psi s, 1 plus psi s, right? And I hope you can solve that equation. You just basically take this guy down here, split it into partial fractions. I'm just going to leave it to you as a homework problem. I mean, I really can't sort of spoon feed you at this point. And you find the solution. So the two steps in between are your homework problem. You find the solution I written down yesterday for the kink. Psi sz is equal to tan hyperbolic z. There's an arbitrariness in terms of where the center is located. So I just put the z0 divided by square root of 2. That's the kink solution. The Dutch function, as I told you, arises often in this these calculations. And basically, you can see as z goes to plus infinity, tan goes to plus 1. As z goes to minus infinity, tan goes to minus 1, basically. And the width over which in these dimensionless units it goes to from one to the other, the size of the steps, typical size of the step, say, that is square root of 2.
And Z now?
Huh?
Z not.
Z naught is just an arbitrary center. I mean, the zero can be located anywhere. It's what's called a Goldstone mode, as a matter of fact. I mean, if you have an infinite domain, you can translate the center any direction. Any doubts? Well, then tell me what is the anti-kink solution? So this is the static kink solution, let's say. Let's just have a sort of a nomenclature. What is the anti-kink solution? I want you students to tell me. The anti-kink solution goes from -1, from +1 to -1. Just the minus of that argument, basically. The anti-kink solution is tanh of minus z minus z0 over square root. And though the derivation is simple, don't underestimate the importance of this calculation. This is what is called, well, I've already used the term kink. It also gets called a soliton, so that is slightly misleading because solitons also have to be stable under collision, and there's no such thing going on here. Or it's also called a domain boundary. The experimentalists usually call it a grain boundary or a domain boundary, or it's called a grain boundary. I think. Whatever. It has umpteen names. Instantol is a nice one. That's from particle physics. And it's basically a solution that is in the vacuum state, as the particle physics say. Physicists say it at both extremes, and somewhere in the middle there's a connection between two vacuums. Okay. So in this language, one side is at this value, one side is at this value, and then the instant torque goes from here to here. Let me give you another example of an instant torque. You have a pendulum. Remember I told you about the pendulum, inverted pendulum? Suppose you flip it, so it's inverted, it's unstable, it flips, and then sort of goes down, 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 and then comes up again, okay? And finally comes back to its up position. How long does that take to happen? Any idea? How long will that take to happen? Time or distance? It actually takes infinite time to happen. In the instant solution, it takes an infinite distance to go from one vacuum state to another vacuum state. Basically, of course, it pretty soon gets to almost +1, but then there are saturation, then there are corrections which are sort of just exponential corrections. You can just get them from here. Okay, and this answers, I think, Jaidev and Punyabhata's question yesterday. The logarithmic growth in one dimension comes from the fact that a kink and an anti-kink are only overlapping by the tails of this, and this tail differs from one by an exponential bit. And then you can sort of write down the evolution equation for the distance between the kink and an anti-kink. This plus an anti-kink is only the solution when they are infinite distance apart. All finite distances will have a small correction.
So that's why two kinks are actually not a stable. I mean, in the sense, not
even a
So
stable
they will
solution,
merge
as a matter of fact. Yeah.
merge.
Yeah. As a homework problem, because this arises in different contexts, to please do this for the pendulum. Okay. Write down the equations of motion of the pendulum, not the linearized equations, the full equations with the sine theta and all that, and try to solve for the phase portrait of the pendulum. You'll learn a hell of a lot by the way. And I'm serious, yeah. Okay. Find out the fixed points, find out the trajectories, find out what in nonlinear dynamics this is called a saddle connection, okay, or a separatrix. So this kind of solution, maybe I'm overemphasizing, but it arises in all contexts. Okay, so now I know that this was either all this or all this is the lowest energy solution, and this guy is a high energy, well, relatively high energy solution, right? What about this kink? That's the next question I want to ask, because that's going to give you the surface tension. Okay, so let's do that calculation also. You here. So the last calculation I hopefully I'm going to do, well, it's not the last calculation, is the surface tension of this kink. So how do I calculate the surface tension? What is the free energy of a solution? G of the kink solution is simply going to be, it changes only in one direction, so it's dz minus infinity to plus infinity times the area, which is the sort of lateral lateral area. So it's just the Ginzburg-Landau expression with psi s plugged in, basically, right? What is the last term? The Landau term plus half d psi s by dz, the whole squared.
This is the constant.
Sorry?
That is the constant.
Which is the constant? Huh? Yeah, no, this is a constant, but this is not the same as that. It's not the same as that. Yeah. But I'm going to exploit the fact that it's a constant. Okay, so that's just a Ginzburg-Landau free energy with the static solution plugged in. Basically, that's all. Okay, and you have to compare that with the Ginzburg-Landau free energy for the homogeneous state, which is simply G psi 0. Let me write it down in the same language because it's convenient. Is A times dz minus infinity to plus infinity. And what is this guy out here? This is minus psi 0 squared by 2 plus psi 0 fourth by 4. And of course, because it's homogeneous, there is no Ginsburg term basically. Okay. So the difference between the free energies, I'm claiming that the kink, I mean, it's intuitively obvious that the kink is going to have a higher free energy, but let's sort of explicitly do that calculation because it's useful to do. So the free energy difference between the kink, yeah, please. This is the free energy of the kink. That depends on space. This is the free energy of the homogeneous solution. Okay, that's the lowest energy of a state. And I'm just going to take the difference of those two to find the cost of introducing a kink. Okay. And I expect that cost to be positive because this kink is unhappy in the interfacial region. Okay. And this is actually a very simple calculation. So let's just spend a few minutes doing it. So this is area minus infinity to plus infinity dz. अब इसको थोड़ा करते हैं ध्यान से. This is going to be minus psi s squared minus psi 0 squared divided by 2. That's that term and that term. This is going to be psi s. I have a reason for writing it down like this. It will become clear in a couple of minutes. That's just psi s 4 minus psi s 4 divided by 4. So that's that term and that term. And finally, there is a surface tension contribution, which is d psi s by dz the whole squared. Okay. So that's the expression for the free energy. Any suggestions about how to proceed? Well, I basically use the fact. I'm going to use the fact that Urna actually pointed out that this guy is equal to 1 by 4th. Okay. But what do I have in here? Basically, I have this guy, but here with a minus sign. Let me sort of just quickly run you through the algebra. Well, it's hardly that complicated. This, if okay, let me reproduce that here. The integral, the first integral is half ds by d squared plus psi s squared minus psi s fourth over fourth is equal to 1 over 4th, right? And 1 over 4th is of course nothing but psi 0 4 by 4 minus it's just psi 0 4 by 4 with a minus sign plus psi 0 squared by 2. I think that's correct. Yeah. So it's basically just that expression with a minus sign. Okay. So this tells me immediately that half d psi s by dz the whole squared. I'm sorry I'm doing this too relaxedly, but anyway, it's worth doing it, is equal to psi s squared minus psi 0 squared. इसको इस साइड पे ले गया तो ये होगा, sorry, this will be minus of that divided by 2. I hope I've done it right. Plus psi s4 minus psi 0 4 by 4. Okay, that's just directly from the integral, the first integral. Okay, but this is exactly the expression I have out here, these two terms. So basically, what you find, Ola, is that this term is exactly equal to that term. Okay, that's the answer I've been going for. So this implies that delta G, the difference in the free energies, is equal to A minus infinity to plus infinity dz, और ये half ये हो गया और half ये हो गया दोबारा, so it's just d psi s by dz the whole squared. And now you can explicitly see, as you expect, that this is some positive quantity. This integrand is positive always. So it adds up to some positive quantity. You can actually find out that positive quantity very easily. It's just a little exercise in integration. What is d psi s by dz? D psi s by dz कहाँ चले गया हमारा psi s? हाँ ये रहा. So this is, forget about the z0. It doesn't matter. It's just a sort of arbitrary center of the thing. So d psi s by dz is x squared. Huh? So I just so that's equal to a minus infinity to plus infinity dz sec both z over root 2, and there'll be some extra factor of I suppose once I take a derivative I'll get a factor of 1 by square root 2, and if I square it up that's going to give a factor. Okay, and this integral you can actually do, by the way. I hope all theorists are familiar with this marvelous book by these Russian guys, Gradstein and Rezek. Have you all seen it? You should open it up and take a look at it. It's amazing the kind of integrals people have solved. Okay, this is actually exactly doable, and that gives you the answer. It's area times 2 square root 2 divided by 3. Nice simple number. Okay. Yeah, I was also surprised that you can actually do that, but you can. Okay, and that gives you the surface tension. The surface tension is delta G divided by the area. It's the cost per unit area, and that in these dimensionless units is 2 square root 2 over 3. Let's put that in the box.
Sanjay, how did you write that step? Like,
which step?
Both the terms are equal to 1/4. So how do you write that?
See, that's just the first integral of motion.
That's yeah.
So that's 1/4. That's fine. Yeah. And exactly the same is true for this, because this is also a good solution.
Oh,
it has to satisfy the integral of motion. Okay. So then I sort of that's why I wrote it in a slightly cumbersome form, just so as to recognize these first two terms. I mean, all this algebra is there in the chapter I've circulated. I mean, even if you don't follow every last line, students, it's okay. You can sort of see how it works out there. Okay. What I want you to do as a homework problem is reinstate the dimensional quantities. ये तो dimensionless है. What does it mean? Surface tension is 2 square root 2 by 3. Okay. I want you to reinstate the dimensional quantities. In particular, find what happens to the surface tension as T approaches Tc. Any ideas? What will happen to the surface tension as T approaches Tc? Huh?
It will blow up.
It will blow up. Huh? You want to think again what happens at Tc? At Tc, the difference between the two phases becomes less and less. So there are no two phases at Tc. So the surface tension will become 0. Okay. So I want you to sort of reinstate the dimensional units and find how it goes to 0. It will go to 0 with some power of T minus Tc, which is not the correct denormalization group result, because this is a mean field theory, but it will give you the correct mean field result. Okay.
Dimension, what happens?
Huh?
Two dimension, third dimension.
Exactly the same thing happens. Huh?
No, it is integral. I mean, probably cannot be
No,
integrated.
no, no. This is for arbitrary dimensions. The kink only varies in one dimension.
Oh, I see.
Droplet is not a static
not
solution.
A static,
not a static solution.
So line basically.
Yeah. So this is basically the kink or excitone is a one-dimensional solution. The droplet, which I'm going to discuss next, will shrink. It's required to shrink. Okay. Okay. Any questions at this point? Then we can take a few minutes off. Huh? Okay, I guess not. Just a couple of things. I had some things, but I'm not going to say them anymore because, again, it's too trivial for you guys. I guess all of you have solved differential equations, right? Have you all solved PDEs on the computer? That's a skill you have to have as a physicist, right? Basically. Okay. So of course the most famous PDE is the diffusion equation. Huh? What is the diffusion equation? It's your good friend del psi by del t is equal to grad squared psi, right? Now you know that if you solve, I mean the crudest way of solving it, but I always use the crudest way, is to just Euler discretize and let it roll. You can do much better, you can do Rage, Tau, whatever they're called, but just the crudest way is to just discretize them in space and time and sort of let them run, I mean, iterate them on the computer. Okay. It's very important to satisfy a condition out here, which is delta t by delta x squared. So that's a condition on the mesh sizes in space and time should be less than half. Are you aware of this condition? You can't take any values of delta t and delta x. You're aware of that, right? Take some sort of resultant value. And this actually goes under a very great name. This is called the von Neumann stability condition. Von Neumann was, of course, one of the pioneers of both computer science and quantum mechanics, right? Absolutely extraordinary human being. Huh? So that's, as I said, it's probably the most trivial thing he did, but nevertheless, it's important for a whole bunch of guys who solve computers. Okay, how does that condition come about? That stability condition. Are you aware of this stability condition? How does it come about? Why do you have this condition? और Neumann बोल दिया तो हो गया. कोई कारण होगा ना? Why do you need such a condition? I'll tell you why you need the condition. You have to make sure that the discrete version of this has the same bifurcation structure as the original differential equation. You should not introduce any spurious bifurcations by discretizing. Okay? And the particular bifurcation you have to worry about is called a subharmonic bifurcation. Anyway, I mean, this is sort of, well, it's not peripheral to the lecture because many of these differential equations actually get solved on the computer. Okay? But there is such a condition, and it comes from requiring that the discrete scheme have the same bifurcation structure as the continuous equation. Okay, so that's the von Neumann condition. There's a similar condition for the TDGL, and I want you to sort of derive it. It's delta x squared, the mesh size, divided by क्या है? Two dimensionality plus delta x squared. तो ये nonlinear equation है. This must be greater than delta t. So when you solve the TDGL equation on the computer, you keep two things in mind. One, you have to pick a delta x that is enough to resolve the kink. Okay, the kink size is in dimensionless units square root 2. So you need to keep delta x less than square root of 2. If you don't resolve the kink, then you won't get the physics right. Okay. Once you have fixed your delta x at some value below the kink width, then you sort of have to satisfy this condition on the delta t. And I want you to derive that as a homework problem. This condition arises for exactly the same reason. You have to insist that the discretization scheme have the same bifurcation structure as the original TDGL equation. Is it clear what you have to do? I think you should derive these conditions. So don't take anybody's word for it, right? Huh? Even if it's von Neumann, you should question why he got that condition. Okay? Okay. So anyway, so as you can see, in higher and higher dimensions, you have to have a more stringent condition on the time mesh size. And that, whatever. I mean, these are trivial to solve on the computer. You just do it on your laptop or some such thing. Basically, you start off with a random initial condition and you watch the phase ordering in time. There's hundreds of such simulations floating around. You can find them in applets on the web and stuff like that. And as long as you satisfy that condition, you're okay. So you have Euler discretization. If you go for a more fancy discretization, the the condition becomes less stringent. Okay. The next thing I want to do, so I've already done, how am I doing time-wise? Okay. I have time. Yeah. I have plenty of time. Okay. Are there any questions at this point of time? Otherwise, I'll move on to the next set of calculations. Now I'll start thinking in terms of what the interfaces are doing. That's going to be the next set of calculations. So अभी मैं क्या समझ लिया? Just to sort of summarize for you guys, ये TDGL equation derive हो गया, हाँ? इसका homogeneous solutions निकाल लिया, which are just 0 plus minus 1. That's almost trivial. And फिर there are a little more work to get distinct solution, which is slightly higher energy than the homogeneous solution, which is why the system would want to get rid of these things altogether. Now I tackle the full-fledged problem, and that's what we're going to do for the rest of this lecture. Okay, the full-fledged problem is how to solve in quotes using all this information, the TDGL equation, and that's going to be sort of my next set of calculations. Maybe I should keep the TDGL equation here. Maybe I should keep the free energy also out here. Yeah. So that is there, there, and psi 0 is equal to 1 in this case. Okay. What is the domain growth process? I have some pictures, but I'll show them at. I've got them loaded, but I'll show them later. The domain growth process is basically something of the following kind. Let's say you have a two-dimensional system. You form domains which are rich in A. Oh, sorry, A is A and B come for binary mixtures. You form domains for the ferromagnet which are rich in up spins at x equal to 0. I'm working at x equal to 0. You form domains which are rich in up spins, domains which are rich in down spins, and whatever. This is another domain that's rich in up spins, and so on and so forth. Okay. The system is equally happy to be in the bulk of one of the phases. Where it's frustrated is at the interface where it's paying a surface tension cost. Okay. So how do these interfaces move? That's the next question. In general, you don't have flat interfaces. You have curvilinear interfaces, as a matter of fact. So how do these curvilinear interfaces move? And I'm going to do a little algebra concerning that also. Again, it's straightforward. If you feel a little uncomfortable with curvilinear coordinates, just ask me. Okay. Don't feel shy to ask. So what I'm now going to do is the following. Let's sort of focus on one particular interface as so. In general, it's curved. It's not going to be. If it's linear, it doesn't move at all. It's a static solution. I mean, it would rather get rid of it, but it's not going to move in either direction by itself. Okay. So this is, let's say, the phase -1, and this is the phase +1. Okay. And now I'm going to introduce a new coordinate system. The new coordinate system, let's pick a point on the interface, has obviously a normal variable n, and you take the direction of n hat as going from the lesser phase to the lesser value to the larger value. Okay? It doesn't matter. That's sort of just a matter of convention. So that's a one-dimensional direction, normal to the interface, and you have a d-1 dimension A vector. Okay, so I've decomposed my d-dimensional space into a coordinate that is a single coordinate perpendicular to the interface at a local point, and d-1 coordinates tangential to the interface at that same point. Okay. Obviously, all the action is going to happen in the n direction. Okay, so the system is sort of homogeneous, so to say, in the a direction. Okay, let's rewrite the TDGL equation in these new coordinates, and some good physics will emerge as a matter of fact. Okay, so for the TDGL equation, I need ये तो ऐसे ही रहेगा, ये h तो 0 हो गया. I need grad squared psi. That's the first thing. Okay, what is grad squared psi in these curvilinear coordinates? First, let's write down grad psi. Okay, it's a little harder to think in curvilinear coordinates, but you get used to it as a matter of fact. Okay, but this is the right way to go because these are the natural coordinates of the system. Okay, as I said, psi only changes in the n direction, so it's very clear what grad psi is. It's del psi by del n. That's the normal coordinate, and at constant t, and then multiplied by n hat. Is that expression okay? Psi is only going to change along the normal direction. In the lateral directions, there's no change. So the grad only has a contribution from the normal direction. Unlike your usual Cartesian or polar coordinates, these coordinates are actually going to vary in space and time. Okay, so that's a little cost you have to pay to do this. Okay, but that's grad psi, and then grad squared psi is equal to, अब इसका derivative लेना है, so this is this multiplied by this. So the first term is going to be del 2 psi over del n squared t, और यहां से एक n hat और आ जाएगा, तो ये हो जाएगा n hat dot n hat, ठीक है, which is just 1 as a matter of fact, right? Plus there will now be a second term where you have to worry about the variation of the normal vector. So the second term is del psi by del n at constant t, divergence of n. Okay? I've just taken the derivative of this guy, and I have two pieces. Obviously, because it's a product of two sort of variables. Okay, so that takes care of del squared psi. The next thing I need is del psi by del t. Okay, for this I'm going to use the following identity, which we're all familiar with. See, psi is in general a function of n and t. It's not a function of a, right? So we're all familiar with the identity. I think we met it in school for the first time. That del psi by del n at constant t times del n by del t at constant psi times, sorry, but I should have taken del, this also works, but I should have taken del n by del psi. I just stick to my notes. Huh? So that's del n by del psi at constant t times del n by del psi. What do I mean? This should have been psi out here. Yeah. At constant t. That's equal to -1. Is everybody familiar with that identity? We've all seen it before, right? Basically. So this guy is बिल्कुल गड़बड़ कर दिया, हाँ? एक मिनट यार, हाँ? This is the problem with this writing it on the board. It's easy on a piece of paper, not so easy on the board. But this should be del psi by del t and constant. I hope that's correct now, huh? Shakuntala, teacher? That doesn't make sense, right? Okay, let me just let me just copy it from my notes and let's convince ourselves it's okay. Huh? So psi is a function of n and t. So the following sort of identity applies: del psi by del t at constant n, del t by del n at constant psi and del n by del psi at constant t is equal to -1. That's okay? Okay. Lesson for the students, never do it think from memory when you teach, okay? Use your notes. Huh? You always get some subscript wrong otherwise. Okay. Okay, तो that's it. ये हो गया काम हमारा. तो मैं इसको तो ये मैं आइडेंटिफाई कर दिया तो इसको del psi by del t is just this term. So it's 1 over that minus 1 over that. And in that language, what is the TDGL equation? इसका 1 over कर दो तो क्या हो जाएगा? Minus del psi by del n at constant t. This is 1 over that. Del n by del t at constant psi. Okay? That's the del psi by del t term. Then psi and psi cubed remain as they are. Psi minus psi cubed. And then h is 0. And grad squared psi is this guy, which is plus del 2 psi by del n squared at constant t plus del psi by del n at constant t grad n. This with some effort, we've written down the TDGL in the natural coordinate system for this problem. The natural coordinate system is this curvilinear coordinate system. It's a little unintuitive. Well, it's actually no, sorry. It's a little intuitive, but a little harder to deal with because the unit vectors are changing in this coordinate line. Okay, but it's going to work fine. What next? Next thing is to realize that at late times the interfaces are locally equilibrated. So you can assume that along the n direction you're actually a kink. Huh? And if you're a kink, then you know that this guy is identically 0 because it's just the solution of the kink. Okay, that's an important sort of assumption out here. Okay, let me make it clearly. It can only be an actual kink if it's a flat interface. Okay, at late times the curvature is sufficiently low that you can assume along the normal direction it's a kink. Kink means it satisfies kink wala equation, and that's just that equation out there, which is why I wrote it in these curvilinear coordinates in the first place. Okay, and that actually gives me my equation which I was targeting.
But these exact, right?
Sorry,
These exact. I mean, it's an assumption, but it's exact, right? Exactly satisfied or
no,
it's an approximation?
a curved interface does not have a kink as a solution.
No, but locally, I mean,
Locally, it's correct, yeah, and it gets better and better at late times, yeah. So you can say
I see.
it's
oh, I see. At long scales, probably.
yeah. So I emphasize that a kink, only technically speaking, is a solution for a flat interface. But
Okay, this is an approximation, but at late stage it will be
it gets better
exact.
and better. Okay, and what else? ये del psi n t ये काट दो. Basically, that you have your answer. What is del n by del t, by the way? It's just a local velocity at this point, right? It's just how you move along the n direction. Okay, so the velocity of the interface at position A on the interface is equal to minus grad dot n hat. This is a very important equation. I think first written down in the context of portioning of soap foam. It applies in all sorts of different situations. And basically what you're saying is the following, that the velocity of the interface is just the local curvature of the interface, basically. Yeah, if you have a flat interface and hat does not vary with distance, the velocity is just identically 0, as we had discussed. But any curvy interface will move with a certain velocity. The more curvy interface, the faster it will move. Okay, why? Because it's very unhappy. If you're on a curvy interface, you are unhappy with your neighbors, right? Basically, because you got neighbors on the wrong side adjacent to you. Okay.
Sorry, which direction? It's on. I mean,
Yeah, that's all. I'm going to say that next. I haven't set the direction yet. So the more curvy the interface, the faster it's going to move. That's one. Second thing is, जो intuitively you can tell me if the interface is popping out, which direction will it move? But it will move to locally flatten the interface. So the sign is got from that if it's popping out, it will move inward. If it's popping in, it will move outward. It will move to locally flatten the. Okay. That's the sort of content of this. I think this is also called. It's a bad sort of name. Allen-Kahn equation. By the way, probably students who are not familiar with the name Kahn. Science of the traditional Martin cyclic transformations, etc., with statistical physics. There are two very well known names in that area. One is Jim Langer, and one is Kahn.
So basically, this is basically the action of Laplacian. It's making the things smoother.
Basically, it's going to become exactly. The system would rather not have interfaces at all, but if it's going to have interfaces, it would prefer to have a flat interface rather than a curved interface. Obviously, between 2 points, a curved interface is a longer distance. The constant surface tension is more. The shortest distance is a straight line. And of course, the next step is to get rid of the straight line also. Okay. Okay, so that's Allen-Kahn equation. And now I'm in a position after all this effort to get a first result from dimensional analysis. If the length scale of the domains is L, it's growing with time, L as a function of t. Velocity is dl by dt. The curvature is 1 over L, and the drive to remove the curvature is sigma. A droplet has a curvature of 1 over L. I'm just going to derive it for you. Okay. And that simply integrates up to give you your first non-trivial result. LT goes as sigma t raised to the power half. Okay. So that gives you your random walk kind of result derived from the Allen-Kahn equation. Sigma is the surface tension. Without surface tension, there won't be any growth at all. The higher the surface tension, the faster the growth. That's the inverse scale of the time, basically. Okay. Are there any doubts about our derivation? Yes, Becca.
Straight, curvature will not move.
Huh?
It will not move straight.
Yeah, if it's a flat interface, it will not move in either direction. See, the way you have to think of it is, does it benefit the interface to move? And if you have a flat interface, if you translate it by something, you don't gain. Is that clear? Well, maybe I should sketch it for you. In a microscopic language, it's a bit clearer. So this is, let's say, the minus sign place, and this is the plus sign. Okay. Now, for the interface to move, even if all these pluses convert to a minus, so it moves over, it doesn't help me energetically. Okay. Equally well, if it moves in this direction, all the minuses convert to a row of pluses, that doesn't help me. Okay.
Can we see from the equation?
Absolutely, better. That's grad L. In this case, the normal vector is uniform in all at all points. Right? That's the unit vector to the interface. Okay. So the gradient of the unit vector is identically zero. Exactly. That's an intuitive way of looking at it. So if this surface is popping out, then okay, if it's popping like that in that direction, let's sketch it again. If it's popping in that direction, let's say these are minuses, and these will be lesser minuses, but and on this side you have plus. Then in that sense, these spins are very unhappy, and it will make sense for the interface to move in. Okay, you will actually gain energy, gain energy terms by doing that. Equally well, if it's popping inwards, again you can sort of convince yourself with a schematic like this. It makes sense to move upwards. Just do a typical square interface in a IC model or something. See what the cost of moving an interface is. Okay. Yeah.
So that sigma there, is that independent of time?
Of course, sigma is 2 square root 2 by 3. It says it's the surface tension, the cost of the interface. The only assumption that's gone into here is that at late times, and this is a very cautious sort of assumption, that basically things only vary along the normal to the interface, and sigma is just the cost of that kink solution. Okay. So the overall cost of this interface will be sigma multiplied by the area of the interface. Okay. Yeah. L is the typical length scale of the domain at time t. That's the characteristic length scale of the domain. If you do a scattering experiment, your inverse wave vector for the peak of the structure factor is 1 over L. Okay, sorry, the inverse wave vector is L. Okay. That's as I told you earlier, if you make a probability distribution of the sizes, obviously they're not all going to be all identical sizes, but it will be sharply peaked or it will have some characteristic scale at which you have an average size. Okay.
So I was wondering, so this is correct for long time span.
This is correct in the what's called the scaling regime. Yeah.
I was wondering if the corrections come from sigma, the log corrections.
No. They don't come from sigma. They don't come from sigma. Right now, I'm just talking of interfaces. I'm not talking about vortices and monopoles and stuff like that. But no, the logarithmic corrections do not arise from sigma. Okay.
Anyway, it is 2 dimensions, right? Specifically 2 dimensions.
This is true for arbitrary dimensions. This is true for arbitrary dimensions. In one dimension, it's not true because you don't have curvature in one dimension, right? So for one dimension, I did a different argument. Okay. Any other questions? Okay, then let's see the realization of this Alan-Khan equation in an example which will sort of hopefully illustrate all the sort of physics going on here. I consider a droplet of size r, which obviously is changing with time because there's growth of the droplet of -1 immersed in a background of +1. I consider a perfect droplet. Of course, there are no perfect droplets in nature, but let's keep things simple. Okay. Now, I want you guys to help me out with this just so as to make sure that I understand it. पहले तो मुझे बताओ n hat क्या है for this spherical droplet. N hat is the unit vector going from the minus phase to the plus phase. So n hat क्या है बताइए? Somebody help me out, guys. It's just but it's just r hat basically. So let's write it in our old familiar Cartesian coordinates. It's x over r x hat plus y over r y hat plus z over r, and let's just write it in 3 dimensions. Okay, ठीक है भाई? Huh? So that's the curvature. Curvature change with time. Sorry, how does it? What is the gradient of the curvature? Somebody help me out with this. Let's take the individual terms का gradients. इस term का क्या होगा gradient? X over r. Del by del x lowest term का. It will be 1 over r, and the second term, there's going to be a second term also. It's going to be minus x squared over r squared. Okay? Sorry, not x squared over r squared. X squared over r cubed. Keep in mind that r is equal to x squared plus y squared plus z squared under the root on the interface. Okay. Again, now I'm working in this new language where I'm doing things only on the interface. Okay. So that's grad n ka pehla term. What is the second term? Plus 1 over r minus y squared by r cubed plus 1 over r minus z squared by r. Simple calculation for a droplet, huh? And of course, you just combine these guys together. What do you get? 3 by r, yahan se, and this will give me 1 over r. So overall, it's 2 by r. Okay. And in arbitrary dimensions, by the way, it's again just dimensionality minus 1 divided by r. Simple exact calculation. Okay. Let's plug this into our equation of motion, the Alan-Carr equation. What do I find? That dr by dt is equal to minus 2 over r in 3 dimensions. Okay. Help me integrate this up. What is the solution? इसका तो बता दो. हाँ? E to the power नहीं है यार. I've already told you, more or less told you the solution. It's going to be something like that only. Huh? Let me write you the exact solution. It simply, this implies, okay, that r at time 0 squared minus r at t squared is equal to 4t. That's the exact answer. Okay. I mean, it's very simple, but it's a very beautiful answer. Let me just put it in slightly different language. This implies that r t squared is equal to r0 squared minus 4t. So if you start off with a droplet of size r0, what is going to happen to it physically? What's the content of that solution? Huh? It's going to shrink uniformly. What is the closure time? The closure time is just dependent on the initial size of the droplet. It's a square root of closure time is the square closure time is just the square of the size of the initial droplet. So again, this random walk sort of picture arises in a very natural way for the shrinking of a single droplet. Okay, but I seem to be much over time already. I haven't still talked about conserved dynamics, huh? But I have one more lecture. Okay, but I still have some more things to say about non-conserved. Anyway, the fact of the matter is that the non-conserved problem is better studied. Has everybody got the chapter I asked for to be loaded? I've written this sort of easily accessible review chapter on phase ordering. Okay, so I think it's been put on the website or something. Okay, okay. So that's okay. So now I've seen that the kink can actually be used to write down an equation of motion for curvilinear interfaces. The last thing is to solve the full-fledged problem, that is the full TDGL in all its glory. And I'm not going to go into the details of that, but yeah, let me just sort of tell you the scheme and how it works. Based again on this scheme. See, in psi language, if you think about it, the kink is not a very pleasant solution. It's a nice looking solution, but it's got a sharp drop from one. It's like a step function basically. If you forget about the distance, okay. So now the question you ask is, can you introduce a continuous sort of variable which goes to the interface? And what the approximation people have made is approximate psi r t by some sigmoidal function of mrt, where m goes smoothly through the interface. There's no step in it. M just goes from minus infinity to plus infinity with a zero at the interface. Okay? And it turns out, and this is called the काफी लंबा चौड़ा नाम है इसका Gaussian auxiliary field. Auxiliary field. I hope that spelling is okay. Or the GAF ansatz. I should also give credit to the guys who did this first. The guys who did this first were Ota, Chasnau, and Kawasaki. Oh, long time ago, they did this. Okay. So again, I'm just going to make the physics to you. Huh? In this language, uh, this guy is a step function typically. This guy is a smooth variable which goes from zero to from minus infinity to plus infinity to the interface. The interface is located at n equal to 0. It was psi equal to 0 out here, the interface. The interface is located at n equal to 0 out here. What happens is the following, that this transformation approximately linearizes the equation, the trivial equation. It's not exact, but it approximately linearizes the equation. And this auxiliary field actually obeys nothing but the diffusion equation. So the zeros of the interface, the zeros of the interfaces are performing random walks according to the diffusion equation. Okay, I'm saying it in a very compact form. There's a amount of calculation that goes with it, but that's the key. Let me again repeat. You start from a continuous your original variable psi. That is a little unpleasant in that it has a step function. You replace it by an auxiliary field, which is a smooth variable going to the interface, and then you find that the auxiliary field. This is approximate, but it's a pretty good approximation. Okay, you find that the auxiliary field obeys the diffusion equation. Now the diffusion equation is something you can solve very easily, right? It's just, if I write down the solution, it's MRT is equal to e raised to power t del squared m or 0. Okay? Have I written correctly? Yeah, that's correct. Yeah, I've just written it in operator format. You know what t raised to power delta squared means, huh? Okay, and the beauty of that evolution is that if you start off with a Gaussian field, it remains Gaussian. Psi, if you start off with a Gaussian field, does not stay Gaussian because it becomes because of nonlinearities. Okay, this auxiliary field stays Gaussian.
Is the way to understand the nonlinear terms will drop out in M?
I think the simplest way to do it is actually just take some sigmoidal function. Sine is painful because you can't take derivatives of it. Take some tangent, take a tangent and substitute it back into the equation. And then you'll find that the nonlinear terms are negligible compared to the linear terms. Okay, so you can back transform that way. I'm saying this very compactly, but it's there at length in my notes, basically. Okay, so this field, and that's why it's called the Gaussian auxiliary field, stays Gaussian for all times. Okay, and Gaussian variables are something we're very friendly with. It enables you to calculate the correlation function psi R1 at T1, psi R2 T2. It allows you to calculate both the equal time and the unequal time correlation function. In this new language, this is simply the expectation value of sine of M R1 T1 times the sine of M R2 T2. Sorry, that's T2. Okay. And the beauty again of this transformation is that though this was a hellish sort of thing to calculate, This one, the function is not so nice. It's a sine function, but the variables are Gaussian. And you can actually push this calculation through. It's worked out over 2 or 3 pages of my notes. I'm just going to give you the final answer for this correlation function. So this is, of course, your good friend, the correlation function, C R vector, and it's a two-time correlation function, T1, T2. Okay, and you can write down the correlation function. It has this sort of rather elegant form, but I have to find it in my notes first.
What is this average over?
The average is over the initial conditions. There's no stochastic element in the evolution. So this average is just over a initial random field psi with e raised to power that applied to it. Okay, but it preserves the Gaussianity of the field. That's a sort of key thing that Ota and all recognize. The answer is simply that C turns out to be, let's write this down carefully, 2 over pi sine inverse of something called gamma, and gamma is the correlator. So this is just because of the sine function. Gamma is the correlator of the auxiliary field, and gamma is simply equal to, if I can find it in my notes, I can find it. It's not the prettiest looking form, but remember it's an unequal time correlation function. It's 2 T1 T2 over T1 plus T2 raised to the power dimensionality by 2 exponential minus r squared over 4d, where d is the diffusion constant, T1 plus T2. Okay. In my calculation, the diffusion constant is this unity. So let me just remove it from here also. Okay. I mean, obviously, I don't expect you to suddenly jump and say, aha, I mean, what a great solution. But I just want to point out to you that this Ochajasko-Kawasaki solution has lots of nice properties which are associated with domain growth. It shows what's called dynamical scaling. Dynamical scaling simply means that the equal time correlation function doesn't depend independently on r and time. The length scale just becomes a scale factor for the length. The characteristic length scale just becomes a scale factor for the distance. So dynamical scaling is a statement that this guy is some scaling function of r over L. It also shows things which have been very popular in the literature, like aging and so on and so forth, that you can calculate. Obviously, once you have an expression like that, you can calculate the aging exponents, etc. So people have thrashed that out a lot already, basically. Okay. Yeah. I said this in a very sort of compact form, but I hope at least up to the before that, all the calculations are clear. This you'll just have to take my word for it. I don't know whether it would particularly help if I solved all these Gaussian integrals on the board. I don't think it's really going to be much use, right? I'd rather talk about. I'd rather show you some evolution pictures in the afternoon.
Do you have a video
Of
simulation? I don't know.
Yeah, I do. I mean, I have snapshots. I mean, yeah, I don't have a video. I have snapshots.
Simulation video.
Huh? A movie would be nicer, probably. Yeah, but like you, Manna, I'm a low tech guy. Well, I don't know whether you're a low tech guy. I'm a very low tech guy. So I'll show you snapshots of the evolution in the afternoon, both for the scalar TDGL and for the vector TDGL, and for phase separation, which again, as I keep emphasizing, is a very different problem. Okay. Yeah. At this point of time, I just want to say that under this approximation, we have a pretty good sort of understanding of how the non-conserved problem works. The basic non-conserved problem, of course, if you put in long-range fields and stuff like that, then all the bets are off. but we understand how the basic non-conserved problem works. We have not been able to complete the same agenda for the conserved problem, the phase separation problem, and that is, an outstanding problem. I'll tell you in the afternoon why we've not been able to implement the same kind of approximation for the conserved problem. Here the interfaces wiggle locally. There the wiggling of one interface is linked to the wiggling of all other interfaces in the system. So it's actually an integral equation. The counterpart of this Kahn-Allen equation is an integral equation with some Green's function. Okay, and we've not been able to solve
So
it.
because of the conservation.
Because of the conservation, exactly. So this interface wiggles. It's not a local fluctuation. Upspin becomes downspin. Okay. This time we have to wiggle. All other interfaces will have to wiggle to maintain the conservation. Conservation law makes problem much harder, and it's a problem we've not been able to solve so far. The only exact solution is the original solution due to Lifshitz and Slezov, which is now like 60 years old, I think. Okay. Lifshitz and Slezov solved the limit where you have a vanishing fraction of one component. And it's a classic paper in the field, and it's probably the most important theoretical work. We do know the growth law, but I'll discuss all that in the afternoon. Yeah, sorry.
There is this expression for gamma. Have you assumed here large T1 and large T2 both?
No, I would just assume that T1 and T2 are in the scaling regime.
Scaling regime, so both have to be large.
Yeah.
Because if T1 I take T1 0, then somehow it is vanish.
Yeah, no, obviously, it's in the scaling regime. Yeah. All the initial transients are gone. Though I've written it down for unequal times, usually the experimentalists look at the structure factor, which is the Fourier transform of the equal time correlation function. They don't, I mean, I don't know, well, they can access some aging properties, but they usually look at the equal time correlation function. So you just put T1 equal to T2 equal to T, and in that form it's a little simpler. Okay, and all sorts of things like Poron law and all that. You know some of this stuff. I think Chankudra, you also played around with it. I talked about that in the afternoon. All sorts of beautiful properties come out of this Ota-Jastrow-Kawasaki function. Okay. So Ota and company did it for scalar case. Bray and I did it for the vector order parameter, arbitrary component, the number of components in the vector. That applies for liquid crystals, superconductors, early universe, etc., etc. Okay. I mentioned that result in
Maybe
okay, sorry, I'm rambling, but any questions? Yeah.
I have just one suggestion. So, since we're running out of class, maybe it would be good if you just write down what is the TDGL equation for conjugate case. We think about it, come back to the next lecture.
Okay, that's a good idea. The TDGL equation for the conserved case is very similar. No, very superficially similar. Sorry, let's get some space on the board. That's a good idea. So I get rid of this guy here. Because it's a conserved variable, you now have a continuity equation. So the order parameter is now a label which tells you. So you're looking at the phase separation of an oil and water mixture. Okay, just to have a name on it. It could be a binary metal alloy of some kind or some such thing. Okay. So the order parameter one should be clear in this case. Psi, if it's +1, it refers to, let's say, oil, one component of the mixture. If it's -1, it refers to water. Okay. So this is a different thing. Okay. The stochastic kinetics is Kawasaki kinetics, where you interchange spins, thereby preserving the number of oil and water molecules. Now the spin up means a kind of molecule and spin down means another kind of molecule. And the resultant equation, if you do on the master equation derivation, is del psi by del t. It's in the form of a continuity equation. Grad J, and basically this. Okay, let me just spend 2 minutes on it. Grad J is a mobility, which in general depends on the order parameter. Grad mu, the chemical potential. I think minus यहाँ कट गया, plus हो गया, ठीक है? and the chemical potential is just that quantity. So that's the final. If you have constant mobility, then it just becomes m squared, grad squared, psi minus psi cubed plus grad squared psi. यहाँ magnetic field का तो concept ही नहीं है, हाँ? There's nothing like a magnetic field in the system. Okay, that's the known in the literature as the Cahn-Hilliard equation. Cahn-Hilliard equation. In the language of Halperin and Hohenberg, that is, I told you they have the most unimaginative names. Model B. Models E and models B are the fundamental equations of domain growth. They are sort of the, so to say, the bread and butter. You can have problems where you have one conserved, one non-conserved order parameter. That's called model, guess what? C. Okay, and then you can have a model which has two conserved order parameters, model D, and etc. 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 Okay, there's a model with a hydrodynamic velocity field. That's a very famous model.
Nowadays we have model B plus.
Model B plus is an active matter model. That's not an doesn't drive you to equilibrium. Yeah, but yeah, I know this model. There's a model B. First there's a active model B, then there's active model B plus. Huh? Gates has been writing nature isko laga ke. Huh? Anyway. So, but those are not sort of yeah, they don't drive you to equilibrium. So this is model B. And the conservation simply comes from the fact that it's a divergence of a current. So if you just integrate both sides of a space, you see that the integral of psi is conserved in time. Okay? And that makes the whole problem substantially harder, except in the limit. See, here you have a question of kitna A hai or kitna B hai. Udhar to ye question nahi tha na, because it could be all up or all down. Here, if you start off with a 50-50 mixture, it has to stay 50-50 for all times. That's what the conservation law means. Or if you start off with a 20-80 mixture, it has to stay 20-80 for all times. So it's solved exactly by Lifshitz's law in the limit where one of the components is 0% and the other is 100%. The vanishing of one component. Okay, and even that paper is not so easy to understand. So, but anyway. We'll talk more about this now. Okay. Any other questions? Play around with the Cahn-Hilliard equation. थोड़ा इसका linear stability analysis वगैरह करके देखो, अच्छा मजा आएगा. I won't go for the Master equation derivation. That will take you a few, maybe a couple of days. But try that. Once I've written down this equation, try its linear stability analysis. What happens to the initial condition? The initial condition is a homogeneous mixture, which is psi equal to 0 plus fluctuations. What happens to the homogeneous mixture? यहाँ पे nucleation and spinodal decomposition and so on and so forth, these ideas will pop in, but I better not, I need to save some energy for afternoon. Any other questions?
I have one small question. M psi is known for Ising class for any say one dimension exactly.
Okay. People generally take M to be constant,
But it depends.
But it actually depends on psi. And if you have a noise, the noise also depends on it's multiplicative noise. It's no longer additive noise. Yes. It depends on M psi. But anyway, that's a separate question. There are only heuristic derivations.
But there is no exact derivation.
There's no exact derivation. I'm aware of at least. Maybe for the diffusion equation, you can have a. You have forms of M.
No, actually, we are trying to.
Yeah. So in this case, the two popular forms are one, it's a constant, and two, where it goes as 1 minus psi squared. So that's the second form, 1 minus psi squared. That's called order parameter dependent mobility. What this does is it cuts out the current in the bulk of the domains. So there's now only current at the interfaces, and that's surface diffusion and surface. So material transport is along the interfaces. And then that opens up a whole new kettle of fish and so on and so forth. Different growth laws.
No, so numerically also it is not known inside. I mean, if I want to calculate exactly, say for in one dimension.
Yeah.
Simplest.
Yeah.
It is not known.
Yeah, I don't even think in 1D. Because in 1D, even the you can't even solve the Kawasaki Ising model. You can solve the Glauber Ising model in 1D, but you can't solve the Kawasaki Ising. Because again of this conservation constraint. I think, yeah, that's true. I think Ray did something with the 1D, but not very successful. Yeah. And then higher dimensions.
Yeah.
Okay. Yeah.
Initially, we started off with, let's say, the Ising model. So we found out that average of SK, the average spin
Yeah.
constants.
Very good.
Then we moved on to the field.
Yeah.
We replaced that average of SK with psi.
Yeah.
Now
Okay.
we have smoothed out psi by a sigmoid of some auxiliary field.
Right.
Now, how do I interpret this? I mean, is it measurable? Can it be?
Well, I mean, if you have these interfaces moving around, see, okay, I'm glad you asked that question. Maybe I should sort of emphasize this. See, the kink goes through the interface as so, right? Psi goes through the interface as so. And this interface is technically located at psi equal to 0. Now, the auxiliary field goes through the interface as so. It's a smooth field. Huh? No step functions anymore. That's why you're using the sine function out here. The interface, so that's the auxiliary field. And the auxiliary field is located at, the interface is again located at any. Okay. And just the fact that you go from the step function to this smooth field makes the problem a lot more tractable. It's not an exact linearization, I emphasize, of the differential equation. Differential equation remains unsolved. Okay. But it gives you a handle. So now the motion of the interfaces is replaced by the motion of the zeros of this auxiliary field. And that has
Are these quantities measurable?
what? The auxiliary field?
The auxiliary field.
Well, if you can measure psi, you can measure m also. Huh? Psi is just, I mean, you can invert it, right? Huh? And you can measure psi. You have a ferromagnet already, you know what domains are plus and minus.
Because the sign.
It's just a sign. But usually, I mean, in general, you write down a sigmoidal function, but the simplest form is a sign.
But for sign, you cannot invert. But phi, you cannot invert.
Yeah. Okay. So let's go for a sigmoidal.
So I think this is the same function that people use for multinumeral for
So what particular neural networks? What particular? I mean, neural networks. All sorts of functions get used.
right, so they replace that step function by
That's.
function.
I think there's some such thing. I'm not very familiar with it now. My knowledge of neural networks dates back to my PhD days when that meant a different thing, basically. Yeah, but they get you use. This sigmoidal function is very common in nature, and as I said, what it does here, it takes this step function and converts it to a smooth field, and somehow that makes the problem tractable. Okay. Doesn't make work in the conserved case because now the auxiliary field can't have a random walk. It has to have a correlated random walk. It has to be correlated with all the other interfaces. So as to conserve the
So
order.
the domains M is independent.
Here it's independent. Right? You can just think of the interfaces as doing local random walks. In the conserved problem, the interfaces have to do correlated random walks. And not just correlated with your neighbor or something, but correlated with the entire system, basically. Any online questions?
I don't see any. So then,
So just ask.
no. Okay, maybe yeah. I'll ask.
Yeah, it's only quarter to one. I really overflowed.
If you have any questions from the online audience, you can ask.
It should be one lecture only. Two is too much.
There's also too much material to
Yeah, too
absorb.
much material.
I hope the students. But anyway, as I said, you don't have to understand 100%. As long as you get 50%, that's good for me. Okay?
Okay, yeah.
So let us thank the speaker.
We'll do the three again, I guess.
Yeah.